All right, you guys, what's up, everybody? We are going to be going over lesson 1.2. Okay, a couple more limits things. We're going to talk about continuity and the intermediate values. Now, before we start, I need to review something with you guys real quick. And the thing that I need to review is everybody's favorite top, factoring. Okay, now there's certain types of factoring. I mean, in general, what we do, right, from its most basic step. You guys know this. Okay, like what multiplies to make 10, adds to make 7, plus 5 plus 2. All right. The ones I really need to review with you, though, are, okay, difference of squares, right? You guys, we write this as, let's call this a squared minus b squared. This comes up a lot, okay, when we're working with limits. It's just because it's one of the easier factoring ones, I guess. We take whatever multiplies to make a squared, we go a times a. Whatever multiplies to make b squared, we go b times b. We go plus minus. Okay, so here's an example. 4x squared minus 81. Okay, so 4x squared would be 2x times 2x. 81 would be 9 times 9 plus 1. That works. All right. Um, you guys, there is no such thing as a sum of squares. You can't factor it. It's impossible. Okay. So meaning if I have a squared plus b squared, you just can't factor that. All right. No such thing as a sum of squares. Okay. Now, the last one I want to talk about, it's quite possible you guys haven't learned this one yet. It's just a memorization thing, so I will show you how to do it. It is called sum or difference of cubes. Now, notice, first of all, it can be a sum or a difference, so not just one or the other. Okay? So the other thing is, it's like, um, it could be like a cubed plus b cubed, or a cubed minus b cubed. Okay, it's allowed to be a sum or a difference. Now, usually when we're trying to memorize the formula, instead of like memorizing two separate formulas because they're really the same, we want to memorize one. What we do is we actually say plus or minus, and whatever I write on the top will be if it's a plus when I write out my formula. Whatever I write on the bottom will be a minus. Okay, hopefully this will make sense. Check it out. The way that you factor this, the first thing you do is you go, okay, a cubed, so whatever it is cubed, you put that here. B cubed, you put that here. And then this sign, you use the same. So if it's plus, you use plus. If it's minus, you use minus. Okay? This is just a pattern. There's really no other way to do it than to memorize this pattern. Here's how it works. Whatever this one is, you square it. Now that should kind of make sense to you guys because look, a times a squared is a to the third. So I hope that makes sense. Okay, whatever this is, you square it. Again, that should also make sense to you because b times b squared is b to the third, right? And then in the middle, what you do is you multiply a and b. Okay, we just go a b. A lot of times, I'll do it like this, and I'll go that squared, a times b, and I'll make a little smiley face. See how cute it is? Look at that little smile. All right. The signs are kind of weird. They go like this. Same. It's the same as what I started with. Here, I'm going to put minus plus because this is actually opposite. So if I started with plus, it's minus. If I start with minus, it's plus. Same opposite. And then this last one is always positive. Okay? So here's another way that we used to teach this. I don't know if it's dumb, but there we go. Same, opposite, always positive. Oh, crazy, right? Same, opposite, always positive. Okay, it's just a pattern. You just got to remember the pattern. Sorry about that. My camera turned off. Hang on. Okay, I'm going to show you two quick examples of cubes, and then we will get started with. All right, so let's go x to the third plus, let's use 27. Okay, so you notice your cubes in this. 1 to the third is 1. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. Those are numbers you're looking for with cubes, okay? 1, 8, 27, 64, 125. Those are your first 5 cubes. So that's normally what's going to show. Okay, here's how you do it. X to the third is what that is. 27 is 3 to the third. We put a plus. Here's how I fill this out. I go square that, join them, 3x. Okay, so x squared, 3 squared is 9, join them, and then I go same, opposite, always positive. That's it. That's my answer, okay? Let's say I do, no, let's do, well, yeah, let's do it. 8x cubed minus, okay? 8x cubed minus 1. Oh, and by the way, I should mention this. When we do a difference of cubes, this part right here, it will never factor. It's impossible. It won't factor down anymore. It always has imaginary solutions. So yeah, this stuff, that never factors. Okay. Okay, so it goes like this. 8x cubed. Well, 8 is 2. X and third is x. The cubed one is 1. Square that. So 2x is 4x squared. Square that is 1. Join them is 2x. And then I just go same, negative, opposite, always positive. The factoring doesn't get too complicated on here. There is one question with like a difference of cubes, so I just wanted to go over that. The rest of the factoring, though, is not too bad. All right, let's go. Let's hit this. Okay, you guys, we're talking about how if we have direct substitution, all right, if we do direct substitution, and we can't get an answer for the limit problem because we have something called an indeterminate. Now, this is important. An indeterminate form is not undefined. Undefined is different than indeterminate. Indeterminate, like, literally means I cannot determine it. Okay? Let me show you guys some indeterminate forms. Indeterminate. I think there are 7. Let's take a look. We usually only use a couple. What are the 7? All right. Infinity over infinity, infinity minus infinity, 0 over 0, 0 times infinity, 1 to the power of infinity. And, let's see what the last one was. 1 to the power of infinity, and, yeah, that's good. Okay? Well, anyway, the one we're going to use the most often, you guys, is 0 over 0. This is really important. This is an indeterminate form. It is not undefined. Not necessarily. I guess it could be. Okay, but it's not undefined. It's indeterminate. All right? And we use algebraic techniques to change the form of the limit, whatever. Okay, first thing, we always start with direct substitution. Or what I'm going to plug that in. So I get, let's see, I get 0 over 0 times 1, which is 0. I told you guys I went and learned at this conference, and there was a lot of AP graders there. And I learned that now limits questions are almost always going to be on multiple choice part. Okay, so this isn't a huge deal. But if it's on the Finner-Swans part, and if you, that is actually incorrect. It doesn't equal 0 over 0 because 0 over 0 is indeterminate. So there are 2 ways we can handle that. 0. What that means is we have to do something else with it. And almost always, the thing that we're going to be doing is factoring and canceling out. Okay? Now look, guys, this one is already factored. Okay, x plus 1, it's already factored. Now, do you notice that I can, okay, I'm allowed to do that. I have the limit as x approaches 0. I'll write it again. 1 over x. Now, if I try to plug that in, I get 1 over 0 plus 1, and I get an answer. This is why this is called indeterminate, because the answer is not actually 0 over 0, and it's not undefined. The answer is 1, okay? But it's a limit. Now, I want you guys to look at this over x. Okay, let's see if I can all right. Let's see. Y equals x over x. Cool. All right. Now we are approaching 0. Okay. Now you guys, if I just try to plug in 0, you guys see right there. There's an open circle there. There's no value at 0. Indeterminate, right? We're going to zoom in a little bit here and see the limit as I am approaching from the left. What number am I approaching? It's getting really close to it. Do you see what number I'm approaching? I'm approaching 1, like 1.0001, right? As I'm going from the right, what number am I approaching? I'm also approaching 1. Okay? So it does not equal 1, but the limit as I get really, really close equals 1. Okay? What I want to tell you guys about what this means is that there is a hole in the graph. When there's a hole in the graph, you guys, so it's like that point, there's a hole. The limit still exists, okay? The limit will still exist right there. Okay, so the limit will exist. What we're doing is we're finding that limit. Now, you guys remember we talked about removable and non-removable? So guess what? The second that we cancel out the 0 over 0 term, right? We cancel that out and we get an answer. He just removed the discontinuity. So we said, oh, let's take. So we're not actually filling the hole. We're just seeing how close it gets without looking at it. Okay? Okay, check this out. Step 1, I try to plug it in. If I plug in 2 and 2, I get 0 over 0. Okay, so I get 0 over 0. So I need to factor this. So the limit as x approaches 2 of x minus 2 over, this is a difference of squares, okay? X plus 2, x minus 2. Now, do you guys see how this crosses out? And what's interesting is this thing that I'm crossing out right here, when I plug in 2, that is specifically what's causing the 0 over 0, so I'm getting rid of that. So it's called a removable discontinuity, right? So I'm pretending that that's not there. And what it means is just that it acts the same as that graph. Okay? So in fact, if I graphed this and this, they are the exact same graph. All right, you guys can try it if you want. They're the exact same graph. The only difference is this one has a hole at 2. This one, the hole gets filled in. And so when I go to plug it in now, I can see that it's 1 over 2 plus 2. So my limit is 1/4. Okay, so what that means is if I graph this initial 1 and I got really, really, really close, I would get to 1/4. There's another way that I can kind of explain this graphing stuff. See if I have TI. Okay, let me just put this up. See if this is gonna work, guys. Hang on. All right, awesome. Okay, so check this out. In my y equals, I'm gonna go ahead and I'm gonna put as a fraction here. Okay, what this was, which was what? X minus 2, x squared minus 4. X minus 2, and then x squared minus 4. On my table, you guys can follow along with me if you want. I'm going to turn this to ask and then auto. Okay, now check it out. The limit as it approaches 2. If I just put 2 in here, it's going to give me an error because that was the 0 over 0. But I want to approach 2. I want to get really close to 2. So what gets really close to 2? 1.9. Okay, 10 over 39, that's weird. 1.99. All right, 1.999. Oh, for goodness sakes, come on. 1.9. There we go. 0.25. Let's see if it goes to the same place from the other side, okay? From the other side of 2 would be like 2.001. All right, that's getting really close. 2.00001.25, right? So I'm getting really close. And it's actually 0.2499999, right? But it's going to get closer and closer to 0.25. And 0.25 is exactly what that limit is. So there's a hole in the graph, but I was able to find it out algebraically without actually using the calculator. Okay? Now this is why I had to go over and stuff because you guys, when I plug in, right, well, here's the thing. There's a difference of cubes, so I got to remember how to factor it. Okay, remember it goes with x and 1, and then we go like this. All right, we go take that squared, and join them. So it's like 1x in the middle. And then for my signs, I go same, opposite, always positive. And there we go. Okay. It's really just memorization, unfortunately. And honestly, guys, it's not going to like show up too much. It's just how you factor cubes. Okay. But look at what happens here. X minus 1, x minus 1. Did I just cancel out the 0 over 0 discontinuity? Okay, so now I'm able to find out where that hole is. Now, when I plug in 1x, I get 1 squared, so I get 3. So this is telling me that as I get really close to 1, the hole is at the point 1,3. The y value will get really close to 3. Okay? Hopefully you guys are good with that. Most of what you're going to be doing after. Okay, now, here's the thing. Let me write this down real quick. All right. So when you get 0 over 0, there's a hole. And what you're going to do is one of two things. You're going to do factoring, or if it is a problem with a square root in it, you're going to do something called the conjugate. Okay? So you can take a break from writing real quick. Let's go and talk about what conjugates are. All right? Let's see. 2 plus the square root of 5. The conjugate to that is 2 minus the square root of 5. Okay? 8 minus the square root of 11. Conjugate to that is 8 plus the square root of 11. And conjugates have special properties. All right. We're going to be able to use the conjugate to kind of make this problem a little bit differently. You've also seen this before, just to relate it. I mean, if you have seen it before, 3 plus 5i. The conjugate is 3 minus 5i, so it works with that too. These ones are called complex conjugates. Okay, but if you ever see that word conjugate, it just means like the opposite, right? Okay, but check it out. What am I telling you to use? All right, so let's say I plug in 1 right here. Square root of 1 is 1, so I get 0 over 0. Okay? But they don't factor, which is kind of weird. So here's what I'm going to do. Okay, so you go and start with the one that has a square root in it, and you multiply by the conjugate. Okay? Now, if it's square root of x minus 1, the conjugate is square root of x plus 1. It means opposite. All right? That on the top and bottom because now I haven't actually changed this problem, you guys, because I'm just multiplying by 1. It's very similar to factoring. bottom. I'm just bottom. That's okay. Now, the ones that are actually the conjugate, those out. Okay? I want you guys to multiply those out. We're going to do FOIL real quick here. All right, now check it out. What's square root x times square root x? So square root x is x. Outside, now look at what happened. The outside is 1 square root x, and the inside is 1. You see what happens with those? They completely cross out. That's actually the entire point of the, okay? Because one's plus and one's minus, the outside and inside always cancel out. And then I just have to put. Now, on the bottom, we are not going to multiply out. Or whichever one is not the conjugate, right? Sometimes it's on the top, sometimes it's on the bottom. We're not going to multiply it out. We're going to leave it separate. Do you see why? So I algebraically manipulated that into this new equation. But look, you guys. Boom, boom. And as x approaches 1, that's my 0 over 0. So now I have this. The limit as x approaches 1, okay, of 1 over the square root of x plus 1. All right. Okay. If I plug in 1 now, I get 1/2. And that's the correct answer to that limit. Okay. Now, let's look at number 5. Always start with direct substitution. Now, I know it says 2 from the right. Don't worry about that for a minute. Let's just plug in 2. Okay. You guys see this is 2 over 0? This is actually not indeterminate. Right? This actually is undefined. But we can kind of answer this in a different way. But it's actually not till tomorrow's lesson, so I don't really know why it's on this page. I basically just to realize that it's not indeterminate, it actually is undefined. So for this particular problem, we're just going to say to be continued because that's actually what we're talking about on the next lesson. All right? All right, sweet. Okay, so hopefully you guys understand that. Basically, 0 over 0 form tells me I have a hole in the graph, and I need to either do factoring or conjugate. Okay? All right, perfect. Discuss the continuity of. All right, well, let's talk about like when we see piecewise functions, right? X is less than a number, X is less than a number. What I want you guys to understand is, okay, so when it says X is less than a number, that means, like, let's say this is my number, it's all this stuff on this side, which means it's the limit as I approach whatever that number is from the left. Less than means I'm approaching it from the left. Okay? That's less than. If I'm greater than, different color here, if I'm greater than all these over here, and right, that's a right hand limit. All right? Okay, if I have x cannot equal a number, you guys, does not equal represents everything but the numbers, so left and right. That's actually both. This is the two-sided limit. Its limit is x of a from both sides. All right? So less than is from the left, greater than is from the right, does not equal both sides. And then anywhere that you see an x equals, that always represents the point. So always just like that exact point. Okay? All right, so let's head over here and, oops, that's our calendar. Okay, and talk about the continuity of, all right. So let's start with this. Does not equal means everything except at the point. Now, why can't it be equal at that point? Well, let's take a look. Let's go ahead and plug in 3 for x. So I get, okay, so I get 3 squared, that's 9, minus 2 times 3, minus 3. So I get 0, and 3 minus 3, 0 over 0. Okay? Now, what we recognize is this says x cannot equal limit as x approaches 3. So let's go back and look at this. Okay, so we know that gave me 0. Limit is x approaches. Go ahead and factor that real. Okay, what multiplies to make 3? Gotta be 3 and 1. Adds to make -2. That's gotta be negative. All right. And then on the bottom, it's just, okay, so I get over 0. And so I have this. The limit as x approaches 3 of x plus 1. And now when I plug it in, I get 4. So I want you guys to, okay, so I can, but basically on the left-hand side and on the right-hand side, this is not what this graph looks like. I'm just making that up. But does that make sense? The limit is 4. But what's actually happening at the point? Okay, this is the point. At 3, the point is at 5. So do you guys think this is continuous? I'm going to say, no, this is not continuous. And the reason is because the limit does not equal the point. Okay? The lines are not equaling up to the point. All right, nice. Let's go ahead and look at this one. Now, this is a little bit different, okay? This right here, x is greater than 2. That's as I approach 2 from the right. All right? X is greater than 2. That's 2 from the right. If I plug that in, I get, because we just start with direct substitution, 3 times 2 squared plus a. I get 12 plus a. That's what that limit equals. All right? Now, this means the limit as I approach 2 from the left. It also represents, okay? Okay, so look, as I represent 2 from the left, or as I approach the left, 2 minus 3 is -1, and the point is -1. Now, let me ask you guys a question. If the left-hand limit goes to -1, and the point goes to -1, in order for it to be continuous, what's going to have to happen over here? Can I go like that? No. Can I go that? No. In order for it to be continuous, it has to meet up at -1. So this one also has to be -1. So can you guys figure out what a would have to be? Okay, good. I didn't trust myself for a minute. A would have to be -13. And as long as a is -13, this is continuous because both sides are going to meet up. Okay? Okay. Just got a little bit more here. Use a calculator to fill in the table to help find. All right, perfect. So let me go ahead on my calculator here. Figure this out. Okay. Here's my equation. So first I'm gonna put alpha fraction. And on the top, I'm gonna go ahead and type this in with me if you guys want. X to the third. X to the third. Okay. Minus 3x squared. Plus x plus 2. And on the bottom, x to the third minus 2x squared minus x plus 2. Okay, and I'm going into my table, set, and again, so auto is just going to do like, 1, 2, 3, 4, so that's not what I want. So I do want to go to ask auto, okay? All right, let me just delete all these. Okay, so let's go ahead and go on my table. I'm going to type these in. You guys can write them down. 0.9. I really would prefer that in a decimal form. That's real annoying. Let's see if I can get this in a decimal form real quick. We only have to go to 3 decimal places, so I'm just going to do that. Float means it'll like float it or it'll automatically convert it to a fraction, I guess. Oh, actually, you know what? Instead of that, 3 means 3 decimals. I'm actually not going to do that. Don't worry about changing this on your guys' calculator. It's fine. I just am tired of that. Answers, we're going to say decimal. Ah, yeah, yeah. Okay, cool. So there's 0.9. I don't have to convert it. 0.99. 0.999. Okay, so hopefully you guys wrote that down. Geez. Okay, so I got 5.736. Just do 3 decimals. 50.749. 500 points. Let's just make sure I type this. Okay, cool. All right. Let's go ahead and go from the other side now. Let's go 1.001. Go ahead and go 1.01 and 1.1. Okay. Let's go ahead and type those in. And okay, perfect. All right, so check this out. Okay. As I am approaching 1 from the left, what's happening to those numbers? They're getting bigger and bigger and bigger and bigger and bigger. Okay. So I can write a statement. Limit as I approach 1 from the left goes to positive infinity. Bigger, bigger, bigger. What's happening is I'm approaching it from the right. The limit as I approach 1 from the right, negative infinity. It's getting, okay. So what's the limit as x approaches 1? Well, this does not exist because what's happening is one side goes to negative infinity, one side goes to positive. I could probably see that on the graph if I wanted to look at it. So see what's happening at 1. One side's shooting up, one side's shooting down. The limit doesn't exist there. Okay? Okay, so let's go back to my table. Now we're going to find the limit as I get close to 2. So it wants me to do 1.9, 1.99, and then 1.999. Okay? And so I get 0.272. I get 0.327 and 0.332. Okay? Let's do one more, even though it didn't ask for it. Just want to see something. 5 nines. Ooh, 0.33333. Okay, cool. Let's go from the other side. So 2.1. Hopefully this is backwards. 2.01. 2.001. Okay, so let me go ahead and fill in that table. So that's 0.384, 0.338, 0.333. Okay. So guys, what's happening as I approach it that way was 0.333, that way 0.333. So the left-hand limit, like this, the limit as I am approaching 2 from the left is the limit as I'm approaching 2 from the right is a third. Guess what? I'm 1. Okay? This says, can a table like these be used to find a limit with absolute? I mean, no, nothing in life is ever absolutely certain, but you can get pretty close. But basically, oscillating functions don't work. We looked at an example of an oscillating function. Can't really do this. Like that's an example of one that wouldn't work. Sine of 1 over x. If I tried to do the limit as x approached 0, it would literally just keep going up and down. You won't be able to find it. Okay? Okay, cool. Last thing I'm going to show you guys real quick, and then this will be done. All right. Okay, so before I teach this to you though, again, okay, I have a line I'm going to draw right across here. Okay, and I'm going to put a point right here and a point right here. All right? And I want you to connect those 2 points without lifting your pencil and without crossing the line. All right? Now, obviously, like that, which I'll pretend like my line, I should have lined this all paper. Okay? The point of this is, you guys, the intermediate value theorem is obviously it's very straightforward. Okay? What it says is, if I'm trying to connect those, no matter how I can, all right, you have to cross at an intermediate value somewhere. I can't cross unless, of course, I were to do this, right? And then I connected them, but I lifted up my pencil, so I was cheating, okay? Or if I did like that and that, like from an asymptote or something, okay? That came to there. It's still cheating, all right? But what the intermediate value theorem says, if you have two and you connect them, an intermediate value has to fit everywhere between the 2 points. But it's a little bit tricky because you have to remember one very super important. F has to be continuous. If it's not continuous, this doesn't work. And what it's saying is it's continuous from A to B. So there's a point there, there's a point. K is any value between here. All right? And it's saying it has to equal K at least one point. Now, the reason it says at least is because it could go like that. It could equal K at like 3 different. But it has to cross that line at least one. That's the point where it crosses. It's very, very straightforward. The biggest thing is continuous. All right. So let's look at number 9. Does the intermediate value theorem guarantee? Okay. Look, f of 0, if I plug that in, is 0. F of 5, if I plug that in, 25 minus 5 is 20. Okay, so question, we got to check for 2 things. Is 12 between 0 and 20? Yes, it is. The other thing we want to talk about is this. Well, guys, the only thing that aren't continuous is like divide by 0, square root a negative number. Okay? That's definitely continuous. So, here's what you check. Continuous, check. 12 between those, check. Yes, the intermediate value theorem works. All right? Now, let's look at this one. Okay, 0 to 3. 0 is negative 4 over negative 2, so that's 2. 3 is 9 minus 4, 5 over 1, so that's 5. And this is asking me if the intermediate value guarantees a value of 4. And I'm like, sure seems like it, because 4 is between 2 and 5. But there's one thing I didn't check. And I didn't check to make sure that this was continuous on that interval. And guess what, you guys? It's not. Okay, look at the bottom. There's a vertical asymptote at x equals 2. So basically, it's like, okay, if I have a point here and a point here, and there's an asymptote, right? That connected them, but there's an asymptote in between. So I actually cannot use intermediate value theorem here because it's not continuous. In fact, I didn't even really have to do that. Immediately I saw it wasn't continuous on the interval. No intermediate value theorem. Okay, now it says find the value of C in example 9a. So we know that we can find a C, so that's good. Now we have to find it. Well, all you have to do to figure out what C is, it says it has to hit that point somewhere between 0 and 5. Take that, set them equal to each other. Okay? So I get x squared minus x equals 12, and I want to see where that happens. Well, you guys, if I subtract that over, actually I get minus 12 is 0, minus 4 plus 3. So it equals at 4 and negative 3. But again, it has to be between 0 and 5. So 4 is my correct answer, not 3. That's the intermediate value theorem. We will go over that a little bit more. Okay, let's talk about how to do these limits. All the way up to this for your homework tonight. Here. Factoring. 9 and 10, I just kind of want you to look at and like think about. Okay. 11 and 12, conjugate. All right. I definitely want to talk about, don't worry about doing it unless you want to look at the graph of it. We'll talk about it. Same with these step functions. I don't know. We'll talk about those tomorrow. And let's just go ahead and say, let's not do, okay? The last part, just to practice a little bit of trig, is all just direct substitution. So figure out what cosecant of 7 power 6, cotangent of power 6, cosine 5 power 3. So see if you can do that. Okay, so next, we want the limit as x approaches 3. Well, the only way it's going to work is if I plug 3 in here, and I plug 3 in here, and they're the same. If they're the same, that's my limit. If they're not the same, it does not exist. Okay? That's what you're doing on 25, and 26. And again, if they're not the same, the limit doesn't exist. Okay? And then, all right, again, this is just like plugging in. Pi from the right is bigger than pi. We're going to do that one. Pi from the left is less than pi. What's the limit as it equals pi? Where if it's the same, that's my answer. But if they're different, the limit does not exist. Okay? A little bit of like best friend stuff, right? For those questions. Let's do these together. Actually, no. You guys can do these. All right. Put this in your y equals, and then on your table, go to like 9, 9, right? So just put those in your y equals and get really close to those points. See what you get. Okay. All right, you guys. So for right now, a discontinuity will occur if the bottom on a fraction equals 0, or I square root a negative. Doesn't look like there's any of those. So bottom equals 0 is where there's discontinuities. Here, the way you check if it's continuous or not, plug that in, see what you get. Plug that in, see what you get. If it's the same, it's continuous. If it's not the same, it's not. Okay? Feel free to skip 40 and 40. And 44. Too much with the step functions, for goodness sakes. All right, we'll do those together. Okay, determine whether the intermediate value theorem would guarantee a C value. Let me show you one of these questions. All right, so first thing I got to do, if this is on 0 to 5, I got to find f of 0, which would be 0 plus 0 minus 1. Okay. I've got to find f of 5, which is 25 plus 5 minus 1. It's 29. And then I just have to check two things. Is this y value somewhere between those? And it is. So that's yes. And then is this continuous? That's a parabola, guys. Yeah, that's continuous. All right. Things that are not continuous are like dividing by 0, square rooting negatives. Okay. Then I'll do 50 with you. It says, okay, cool. Now that we know, oh, so the answer was yes, we can use the intermediate value theorem. Now that we know that, find the C value. Okay, well, the way I do that, now that I know I can use the intermediate value theorem, is I take that, go to that, and I solve. I subtract that over, what's that? Plus 4 minus 3. And so I end up getting negative 4 and 3, and the interval is 0 to 5. So, okay. So skip the ones I told you to skip. Go ahead and do the rest of those, though. Hopefully that helps. Go over it when I get back, and I see you guys next. All right. See you later. Have a great day, guys.